What if I told you the very center of our planet shouldn't exist? Not the way you were taught, not the way any physics textbook describes it. Because the core of the Earth is doing something that breaks the basic categories we use to describe matter itself. And scientists have only just figured out why. We all learned the basics in school. The Earth has layers: a crust, a mantle, a liquid outer core, and a solid inner core. Clean, simple, tidy. Except the deeper we look, the messier it gets. Because the solid inner core is behaving in ways that are frankly bizarre. It transmits certain types of seismic waves far too slowly for something that's supposed to be a giant crystalline ball of iron. And for decades, nobody could figure out why. The answer, it turns out, involves a state of matter so strange that it almost sounds like science fiction. Something that is simultaneously solid and liquid at the same time. Not solid on the outside and liquid on the inside. Not alternating between the two, both at once, in the same material, at the same moment. We're talking about a phase of matter called the Superionic state. And a brand new experiment has just confirmed for the first time in a lab that iron can actually enter this state under the right conditions. Conditions that happen to match almost perfectly with what exists right now at the center of our planet. So today, we're going to walk through the whole story. How we discovered Earth's interior without ever being able to see it or touch it. Why the data started breaking down the cleaner it got. What this exotic state of matter actually is, and why this discovery might change how we understand everything from our planet's seismic activity to the very magnetic field that keeps us alive. Stay with me, because this one goes deep. And I mean that literally. The story begins with a simple problem. We cannot see inside the Earth. Light doesn't pass through rock, obviously. And no drill humanity has ever built has come close to reaching the deep interior. The deepest borehole ever created went about 12 kilometers down. The distance to Earth's center is over 6,000 kilometers. We're not even close. So how do we know anything about what's down there? The answer is that we listen. Earthquakes send shock waves rippling through the planet in all directions. These waves travel at different speeds depending on what they're moving through. And when they reach the surface on the other side of the world, seismographs pick them up. By analyzing the timing, the speed, and the behavior of these waves, scientists have been able to build a picture of Earth's interior the same way a doctor uses an ultrasound to see inside the body. Two types of waves matter most here. Primary waves, or P waves, are compression waves. They squeeze and stretch the material they move through, and they can travel through both solids and liquids. Secondary waves, or S waves, are shear waves. They move material sideways, perpendicular to the direction of travel. And here's the key thing about S waves. They cannot travel through liquids. A liquid doesn't have the structural rigidity to propagate that kind of sideways shaking. In 1914, a geophysicist named Benno Gutenberg noticed that S waves from earthquakes disappeared on the opposite side of the globe. They vanished into a shadow zone. The only explanation was that they were being blocked by a liquid interior. Earth had a molten core. Then, in 1936, a Danish seismologist named Inge Lehmann noticed something strange within that liquid region. Some P waves were showing up where they shouldn't be. They were appearing inside the shadow zones. She worked out that they must be bouncing off a solid object buried inside the liquid core. A solid inner core, floating at the heart of a liquid outer core. A discovery that came years after we'd already figured out the universe was expanding. Since then, our seismic technology has gotten dramatically more sensitive. We've deployed monitoring networks across the globe. We've refined our models, and the basic layered picture has held up remarkably well. Crust, mantle, liquid outer core, solid inner core, mostly iron, clean, elegant. Except when the data got cleaner, the picture got messier. Here's where things start to unravel. As our seismic instruments became more powerful, scientists noticed anomalies in how waves travel through the inner core. P waves move faster when they travel pole to pole compared to when they travel along the equator. That's a directional asymmetry. Crystalline materials can behave this way because the speed of sound through a crystal depends on which direction you travel relative to the crystal lattice. So, a global alignment of iron crystals in the inner core, organized along Earth's rotational axis, could potentially explain that difference. Fine. But then there's the bigger problem, the S waves. Remember, the inner core is solid, so it should support shear waves. And through conversion processes at the boundaries, P waves entering the inner core can partially convert into S waves, travel through, then convert back. Incredibly, we can actually detect these waves at the surface. And here's the problem. Those S waves traveling through the inner core are way too slow. Far slower than what you'd expect from crystalline iron at those pressures and temperatures. They're also losing energy much faster than they should. Something inside the inner core is making it softer than it should be, squishier, more pliable, almost rubbery. Scientists have a way of measuring this softness called Poisson's ratio. It captures the relationship between how resistant a material is to compression versus how resistant it is to being sheared sideways. For most solids, this ratio sits somewhere around 0.2 to 0.3. For rubber, it's close to 0.45. For Earth's inner core, seismic data puts it at around 0.45. Let that sink in. The supposedly solid iron core at the center of our planet has a mechanical signature closer to rubber than to steel. Something is wrong with our model. So what could explain this? Scientists have explored a few possibilities. The first was alloying. Iron in the real Earth isn't pure. There are lighter elements mixed in: hydrogen, carbon, oxygen, silicon, sulfur. Adding impurities to a crystal lattice can change its mechanical properties. Maybe the right combination could push the Poisson's ratio higher and slow down the S waves. But when researchers ran the numbers, even generous amounts of these lighter elements didn't produce enough softening on their own. The second idea involved grain structure. When molten metal solidifies, it doesn't typically form one giant perfect crystal. The solid forms from multiple starting points simultaneously, growing outward until the different regions meet. The result is a collection of misaligned crystal grains, each internally ordered but oriented differently from its neighbors. The boundaries between these grains are weak points. They can slide. If thin films of partially molten or softened metal form along those boundaries, it would add a layer of lubrication that slows down shear waves and increases energy loss. This grain model can explain some of the observed properties, but it doesn't fully work either. There's only a very narrow range of grain sizes and melt fractions that produces results consistent with the seismic data. Go slightly outside that range in either direction and the model breaks. Either the core becomes too rigid or it loses energy way too fast compared to what we observe. And there's another problem. Fine-grained structures are less likely to organize themselves into globally aligned lattices. But we need that global alignment to explain the polar versus equatorial speed difference. The grain model creates as many problems as it solves, so the obvious explanations don't work, which means the answer has to be something stranger, and it breaks one of the first rules you were ever taught in chemistry class. The rule that says matter is either solid, liquid, or gas, because what's actually happening down there is none of those, and all of them at the same time. What we need is something more radical, something that keeps the large-scale crystal structure of the core intact, allowing for that global alignment, while simultaneously introducing a fluid-like softness that brings the Poisson's ratio up to the observed value and slows down those shear waves. In other words, we need a material that is somehow both solid and liquid at the same time. And that's exactly what the Superionic state delivers. In a Superionic material, you have two distinct components behaving in completely different ways within the same substance simultaneously. One component forms a rigid, structured crystal lattice. It stays in place. It provides mechanical rigidity and maintains the overall shape of the material. The other component, a different atom or type of molecule living in the spaces within that lattice, is mobile, freely mobile, moving through the lattice the way atoms move through a liquid, essentially conducting or flowing while the surrounding structure stays fixed. The material is simultaneously crystalline, solid, and liquid, depending on which component you're looking at. This isn't just theoretical. We already know this state exists in other systems. There are various Superionic materials in practical use today, in batteries, fuel cells, and sensors. And famously, we've confirmed the existence of Superionic ice, where hydrogen atoms move freely through an oxygen crystal lattice at high pressure and temperature conditions. It's a well-established phase of matter. We just didn't know until recently whether iron could enter it. For Earth's inner core, the proposal is that iron, alloyed with nickel as we already know it to be, forms the rigid crystal lattice, and lighter atoms like hydrogen, oxygen, and especially carbon sit in the gaps within that lattice structure. At low temperatures, carbon atoms would stay put, locked in fixed interstitial positions. But molecular dynamics simulations showed something remarkable. As temperature increases, carbon atoms start hopping between those positions, and above a certain threshold, they transition fully into liquid-like behavior, moving freely through the iron lattice while the iron itself remains crystalline. According to those same simulations, the pressure conditions inside Earth's inner core are exactly what's needed to push an iron-carbon system into this Superionic state. And when the simulated Superionic iron-carbon material was tested computationally, it showed lower shear wave velocities than pure iron and a Poisson's ratio of around 0.43, remarkably close to the observed value from seismic data. Simulations are powerful, but they're not enough on their own. You need experimental confirmation. You need to create the conditions in a real lab and measure what actually happens. And that is exactly what a research team led by Huang He and Zhang set out to do. Their approach was, to put it plainly, beautifully extreme. They created an iron-carbon alloy in the appropriate hexagonal close-packed crystalline form. Then they accelerated a projectile at it using something called a light gas gun. Here's why a light gas gun is special. In a standard firearm, the maximum velocity of the projectile is ultimately limited by the speed of sound in the gas behind it. Gunpowder produces expanding hot gas, and the bullet gets pushed by that expansion. But sound speed depends on the molecular weight of the gas. Air, which is mostly nitrogen, sets one limit. If you replace it with hydrogen or helium, much lighter molecules, the speed of sound goes up dramatically, and you can push a projectile significantly faster. Light gas guns can launch projectiles at over 20 times the speed of sound, fast enough to match orbital velocities. These devices are used to simulate micrometeorite impacts on spacecraft hardware. And in this experiment, they were essentially being used as a particle accelerator for geology. When the projectile struck the iron-carbon sample, it created a shock wave. That shock wave generated pressures and temperatures high enough to potentially unlock the Superionic state in the alloy. Then the team used a technique called photon Doppler velocimetry to study what was happening inside the compressed material. This works similarly to the way a speed gun operates, but with extreme precision, measuring surface vibrations that reflect the internal properties of the sample. It's seismology at laboratory scale. What they found was consistent with Superionic iron. The shear velocity of the material dropped. The Poisson's ratio climbed. The values matched what the simulations had predicted and what the seismic data from Earth's actual inner core has been showing for years. Now, to be transparent about the science here, the experiment didn't reach the full pressure and temperature of Earth's inner core. The conditions were extreme by any laboratory standard, but they didn't fully replicate the real thing. What the experiment did do was demonstrate that this superionic state can exist in iron-carbon alloys at all. It's a real experimental confirmation of a phenomenon that had only lived in simulation until now. And it's a strong signal that Earth's inner core is doing exactly this. That right now, kilometers beneath every earthquake, every ocean, every human being on this planet, there is a ball of crystalline iron with carbon atoms flowing freely through its lattice, solid and liquid, simultaneously, in a state of matter that doesn't fit neatly into any category we teach in basic chemistry. If stuff like this is why you fell in love with science in the first place, consider subscribing. It genuinely helps me keep digging into the discoveries most people are missing. If the Superionic hypothesis is correct, it opens up explanations for several other mysteries that have been sitting uncomfortably in geophysics for years. The polar equatorial speed asymmetry, for instance. In a Superionic core, the mobile carbon atoms wouldn't flow randomly. The conditions inside the core, including Earth's rotation and internal heat flows, would bias the carbon flow preferentially along the rotational axis, pole to pole. That directional flow could itself account for some of the speed difference without requiring perfect global alignment of the iron crystal lattice. It relaxes a major constraint that the pure crystal model had struggled with. But the most startling consequence of this discovery has nothing to do with seismology at all. It might explain why life on Earth is even possible in the first place. The geodynamo, the mechanism that generates our planet's magnetosphere, depends on the movement of electrically conductive material in the outer core. But the nature of the inner core's interaction with that process has always been somewhat murky. If carbon is flowing through the inner core in a liquid-like manner, that movement of charged particles could contribute directly to the geodynamo effect. The inner core wouldn't just be a passive solid passenger inside a churning liquid core. It could be an active participant in generating the magnetic field that deflects solar wind and makes life on Earth possible. Think about what that means for a second. The fact that our compasses point north, the fact that our atmosphere hasn't been stripped away by radiation over the last 4 billion years, might be partly due to this exotic state of matter at the planet's heart. Carbon atoms flowing through an iron crystal, in a phase that's simultaneously solid and liquid, maintaining the magnetic shield that wraps our entire world. There's something deeply satisfying about how this story comes together. For over a century, we've been building our picture of Earth's interior from the outside in, listening to the echoes of earthquakes and working backwards. Each new generation of instruments revealed new anomalies. Each anomaly pushed us towards stranger explanations. And the strangest explanation of all, a material that breaks the boundaries between solid and liquid, turns out to fit the data better than anything simpler. The cosmos, it turns out, doesn't do simple. Not in the hearts of stars, not in the fabric of space-time, and not in the 6,000 kilometers of rock, metal, and now apparently exotic phase transitions sitting beneath our feet. We've been studying the universe for long enough to launch probes past the edges of our solar system. We can detect the light of galaxies so distant that it took over 10 billion years to reach us. And yet the interior of our own home planet has remained stubbornly, humblingly mysterious. But that's changing. Not by drilling deeper or sending probes downward, but by smashing matter together in labs, by running simulations at atomic scales, and by listening more carefully than ever to the planet's own voice. Earth has been talking to us through seismic waves for billions of years. We're finally starting to understand what it's been saying. The core isn't just solid. It isn't just a dense iron ball frozen in place since the solar system formed. It's alive in its own way, flowing and rigid simultaneously, moving and still at once. A state of matter that had no name until we needed one to describe what was happening at the center of everything. And that's where we are. Standing on top of a planet whose heart operates by rules we're only now beginning to decode. Now, if this one rewired how you think about the ground beneath your feet, the video on screen right now goes even deeper into the mysteries science is just starting to crack. Go ahead and click it before it disappears, and hit subscribe on your way in so you do not miss what comes next. Stay with me. There is a lot more buried just below the surface. I will see you in the next one.